Hello everyone, I am B. Sister Reddy from ECEA section. Today I am going to give a seminar about latches from the subject switching theory and logic design. Latches are devices designed to securely fasten and hold objects together. Overview of latches. Latches are fundamental components in digital electronics, particularly in the domain of sequential logic circuits. Unlike combinational logic circuits, outputs uh, which produce outputs only based on their current inputs, whereas sequential circuits rely on memory elements to store past states. Latches serve as these memory elements capable of storing a single bit of information. They are bistable devices, meaning they have two stable states and can maintain a state indefinitely until an input triggers a change. This property makes them essential for applications requiring data retention such as registers, memory units, and control systems. Latches are typically constructed using logic gates and are sensitive to input changes, making them suitable for tasks like switch debouncing and temporary data storage. Understanding latches is crucial for grasping more complex sequential components like flip-flops and counters. There are types of latches: SR, D, JK, and T latches. Let us have a brief introduction. There are, as I told, there are four types of latches, each designed to perform specific functions within the digital systems. The SR latch is the most basic type, where SR represents set reset. It uses two inputs to set or reset the output. When S equals to 1 and R equals to 0, the output Q is set to 1. When S equals to 0 and R equals to 1, the Q is reset to 0. Whereas the D latch simplifies the SR latch by eliminating the invalid state and ensuring the output follows the input when enabled, where D represents data or delay. The JK latch is an enhancement of SR latch, allowing toggling behavior when both inputs are high, thus avoiding the indeterminate state. The toggle, where T represents the toggle, uh, with the T latch changes its output state whenever the input T is high and making it useful in counters and toggle operations. Each latch type has unique characteristics and is chosen based on the requirements of digital system design. Understanding these types helps in selecting the appropriate latch for specific applications. Let us see functional behavior of latches by their truth tables and circuit diagrams. Let us discuss functional behavior of their latches. Truth tables and circuit diagrams are essential for understanding their functional behavior of latches. The SR latch truth table shows that when S equals to 1 and R equals to 0, the output Q is set to 1. When S equals to 0 and R equals to 1, Q is reset to 0. When both are 0, the output remains unchanged. The D latch has a simpler truth table where the output Q follows the input D when the enable signal is active. The JK latch combines the features of SR latch, includes a toggle condition. If both J and K are high, the T latch has a truth table indicating the output toggles when T equals to 1 and remains unchanged when T equals to 0. These circuit diagrams visually represent the internal logic gate connections that realize these behaviors. They help in designing and analyzing digital systems by providing a clear view of how inputs affect outputs. Mastery of truth tables and circuit diagrams is crucial for implementing and troubleshooting latch-based circuits. Here we can see the SR latch. See, there are two NAND gates with the clock, which enables the inputs, and these inputs where depending on the outputs of the CQ is Q and Q bar. As we discussed before, S equals to 0 and R equals to 0, we get, and it is unchanged. Then in next state, 0 is set to be 0 and 1 is 1, where at 0 and 1 inputs of S and R respectively, we get 0 for any value of Qn. See, for 0 it is 0 and for 1 is it 1. And for S 1 and 0 values of S and R respectively, we get 1, which is set to be set. For Qn 0 it is set to 1 and 1 also it is set to 1, where at high values it is undefined. Where the D latch, here also the clock is same, and it is similar to the SR flip-flop where there is a change at S and R in place of D and D bar, where D mean to be a data. When D is 0, Q is 0, then next state is also 0, which means it is unchanged when the D value is, it is 1. It is 0 when the D value is 0, and 1 if the D value is 1. In the next state we get 1. Here 0 and 1 of the D values represents reset and set. For JK latch. For JK latch, as we said, J and K are interchanged with S and R. It is similar as SR latch, where we get where we where it is also defined and toggled at high values of J and K. For 0 and 1, it is complement of in the present state of input. Let us go to T latch. In T latch, if your input T value is 0, the next state is unchanged. If your T value is 1, it is changed, which is meant to be for the T value 0, it is Q. For T value 1, it is Q bar. For 0, it is itself, and for 1, it is complement. Let us see applications and practical uses of latches in digital systems. Latches are widely used in various digital systems due to their ability to store and maintain binary states. One common application is in registers where multiple latches are combined to store multi-bit data. They are also integral to memory units, serving as the basic building blocks for storing information. In control circuits, latches help to maintain the state of control signals, ensuring consistent operation. Another practical use is in debouncing mechanical switches, where latches filter out noise and prevent false triggering. Latches are also used in timing circuits, data synchronization, and temporary data storage during processing. Their versatility and reliability make them indispensable in digital electronics. Understanding their application helps in designing efficient and robust digital systems that require state retention and control. Let us have some quick summary and key takeaways from this topic. Latches are essential components in switching theory and logic design, serving as memory elements in sequential circuits. They store one bit of information and maintain state based on input conditions. Various types of latches, including SR, D, JK, and T, offer different functionalities suited to their specific applications. Understanding their truth tables and circuit diagrams is crucial for designing and analyzing digital systems. Latches are used in registers, memory units, control circuits, and switch debalancing, highlighting their importance in practical digital electronics. Mastery of latches concepts lays the foundation for more advanced topics like flip-flops, counters, and sequential logic design. This summary encapsulates the fundamental aspects of their latches and their role in digital systems. Thank you.